Hi, my name is Kirby Rayner, and my project is entitled Reinforcement Learning with Quanzer. Now, this project was done as part of Learning Meets System and Controls at University of Houston, Cullen College of Engineering, spring 2024, under the direction and instruction of Dr. Sasan. Now, the goal of this project was to investigate some common reinforcement learning algorithms for control on a nonlinear rotational inverted pendulum. We had access to a high fidelity digital twin provided by Quanzer. Now we wanted to try some reinforcement learning algorithms for control of that system. And really, we just want to investigate some training, some hyperparameter tuning of some common reinforcement algorithms and utilizing them on some real world systems or digital twins. Now, for the environments, we did this project in MATLAB and in Simulink. Quanzer over here, they have this hardware, Cube Servo 3, which is a rotational inverted pendulum, along with some other real nice hardware. But this is the hardware reason for this project. They also have a digital twin. Now, both the hardware and their digital twin can be accessed, interfaced, and controlled through Simulink. We're using MATLAB, Simulink, and the digital twin from Quanzer for this project. Now, algorithms. For this project, we wanted to investigate just some common, very popular RL algorithms. We wanted to compare both off-policy algorithms and on-policy algorithms. The choice of some of these algorithms was also inspired by a previous semester's project. Some of these, during a previous semester, another group had a lot of successes with some of these algorithms, and that's the choice for some of these algorithms. Now, the first one is a deep deterministic policy gradient, DDPG. Put very simply, it's Q-learning for continuous action space. Now, one thing about DDPG is it can be brittle to certain situations, and it can overestimate Q values. Now, to fix that, they've created an extension of DDPG, which is twin delay DDPG TD3, which aims to quit overestimating the Q values. And this algorithm here is one of the algorithms that had a lot of success during the previous semester's project. Some of the three key features of this algorithm is it utilizes clipped double Q learning. So it takes two Q values and takes the minimum of those two Q values to try and limit Q value overestimation. It also has delay of the policy updates and target policy smoothing. For on-policy algorithms, we just have a proximal policy optimization, or PPO for short. And this algorithm directly optimizes policy to maximize the expected reward. Now, for comparison of the RL algorithms, to the right, you see a kind of tree, which gives a generalization of some of these more common algorithms. All the algorithms we worked with this project are on the left. So, the algorithms that we mentioned, both are actor-critic. Both are policy gradient methods, both the DDPG TD3 and the PPO. PPO attempts to improve the same greedy policy used for exploration, so on-policy algorithm. The DDPG and the improvement, the TD3, has a behavioral policy and a target policy. And one thing it does is while it's running, it holds on to a experience buffer, a replay buffer, and it samples that with batches. And that way it's sampling a diverse set of recent experience. We will also get into reward hacking, and I want to draw your attention to this video in the right hand corner that kind of shows the example. And you see this in this simulation. This humanoid was to throw a ball towards a red square, and you see it starts running the ball there. It's a very, very great example, great visualization. So reward hacking is a phenomenon where optimizing imperfect proxy reward function, the one that you wrote, or the reward function you have weighted, leads to poor performance with respect to the actual reward function. And when you should have wrote, the weights you should have, and put simply, you don't get the behavior you want. You get this humanoid running a ball to the red square. And that's something that can happen when training RL agents. You can get some behavior that's not the behavior you intended. We're also going to talk about model bias. One thing you have when training RL algorithms is you can use a model to train the RL algorithms. There are several different reasons for doing this. It can be very efficient. It can speed things up. It can be safer. If you're training RL agents on a model, if the model's close enough or your RL agents are flexible enough, there are little to few issues when you move on to the actual real world system. But again, you do have an agent that is optimized with respect to the model and not the actual system. So our methodology, you can see it here. This is where we worked for this project. I guess we're going to start at the top. At the top, what you have is a nonlinear inverted pendulum closed loop system. Now, feedback of the closed loop system is the observation. You have observation is fed to the reward function that we have engineered, and it goes back to the agent. In that top Simulink block, you can also see the agent in the very top right. The agent takes an observation, takes in a reward, can have local stop training criteria in the Simulink model, and the agent adjusts the control signal. So that is our model. From there, what we have is basically the same system. We still have an agent, only this time, instead of controlling a model, it's controlling the actual physical high fidelity virtual twin of a rotational inverted pendulum shown to the right. And it does this through the block that you see in the top left hand corner of that bottom Simulink model, right here, through that HIL block. The HIL block is hardware in the loop, and it can interface to their digital twin or to their actual hardware. So something that's real important about this system is the reward function. For this system, we used a quadratic regulator reward signal. So what you have is you have three different variables for this rotational inverted pendulum. You have the angle of the pendulum itself, you have the angle of the rotary arm, and you have the motor voltage. All those variables are squared. Also, the velocity of both angles are also squared, and we have those weighted. And we have a negative sign out front, and what we're trying to do is maximize that reward signal. Something else that we also have a penalty built into this. There is some undesirable behavior that you don't want out of this system. You may not want the servo to drop the inverted pendulum. You may not want motor voltage to over voltage, or you might not want saturation. As something that's real important and relevant to our simulations, we did not want the rotary arm to allow this thing to cross its own wire bundle. So all those terms are attached to a penalty factor that's part of the reward function. Now, that penalty factor can also additionally be tied to stop training criteria to locally stop the episode of the training session if you get that undesired behavior. So, for the networks, we used just default networks and default network depths. Now these are all shown. The top are the actors of the system. The bottom are the critics. This network geometry is what MATLAB Reinforcement Learning Toolbox just default pulls out. Now, throughout this project, we did not change this geometry. We did not change the depth. One of the reasons this is not done is based on a previous semester's project. For their project, they found that increasing the depths did not help, but they had better results from changing the widths and adjusting the hyperparameters. So when we go to adjust the hyperparameters, we will also adjust the widths. We never mess with the depths, and these are the networks that we use through all the training sessions. These were started with a default layer size of 256, an Atom solver, at 10 to the 4 experience buffer for the off-policy algorithms, batch size of 64 for the off-policy algorithms, and a learning rate of 0.01 across the board for actor and critic. The results. We started with the DDPG algorithm, and you can see in the right-hand corner the Cube Servo 3 is balancing that inverted pendulum no problem. We had 100 episodes, 0.01 sample time, and the simulation was ran for 2 seconds, which means max steps per episode was 200. Stop training was average reward. We always kept it between -30 and 0. We didn't vary it too much for any of our training sessions. We might for future work. The total steps are 125,000. One thing you'll see is the total steps is less than the max steps per episode over all episodes, and that's due to the stop training criteria within the model. This was trained on the nonlinear inverted pendulum model. Something else that you have for training these algorithms, at the start of each episode, the pendulum has to be initialized. So we have a reset function programmed, and we can change where it initializes it. For balancing the pendulum, we just initialized it within 10 degrees of full inverted. As you can see, it trained no problem. Now, to get that in the control loop for this video, we have it where the control system does not click in until we manually turn the pendulum arm within 10 degrees. The control system clicks in, and that's something else we could vary as we compare swing up and balance versus just balance. Now, having a successful DDPG algorithm that could balance the pendulum, we wanted to try and swing up and balance. And these videos to the right, the top one is a successful swing up and balance. And the bottom one is a unsuccessful. And we're gonna go into some of the details of what was successful, what wasn't, and why. Now for the training criteria, we know we're training in a wider envelope, a more complicated task. We're gonna need more episodes, 2,500 episodes, 0.01 sample time, 5 seconds, which means there's max steps per episode of 500. Stop training is still the average reward. Total steps, 850,000, which is less than total steps that could be achieved. That's because of the reset function. That's because of the stop training criteria within the simulation. Now the reset function. What worked is what's highlighted on that unit circle. Initializing the inverted pendulum within 20 degrees of full inverted over that training criteria for DDPG, default depth and width worked. What other things we tried is we initialized it, had the reset function initialize the pendulum throughout this entire range. We also initialized it towards the bottom. The video you see on the bottom is actually one of those training sessions. The start of each episode, the pendulum started near the bottom. As you can see, this agent was trained to swing and try and get the pendulum higher, but it could never quite get the pendulum high enough to swing up and balance. Again, what worked? 20 degrees of full inverted for this algorithm. From here, we have a working DDPG for all tests. We tried moving on to the other algorithms. And that's where we started getting some undesired behavior, and we're going to reward hacking. You see these three scopes. The first one's motor voltage, the second one's rotary angle, and recall we have some undesired characteristics in the envelope we don't want it going into. We don't want it to clip its own wire bundle. You also have the pendulum angle. Now you can see from this, the pendulum angle 0 is full inverted. This algorithm is balancing this inverted pendulum on this nonlinear model. However, looking at middle scope, it's doing that by going outside or to the border of the envelope we don't want it to break. Something that can be noted, you can adjust that window and adjust the stop training criteria. So to help disincentivize it going in this area wasn't for this training session. So there's future work to try and limit this behavior. Both TD3 and PPO bound this way to balance this inverted pendulum. And we're going to show some videos here. Very interesting behavior. First video is just TD3 on balance. You can see it tries to do that reward hack behavior, go to the edge of the rotary envelope and balance the pendulum. And it can balance the pendulum for a while, but eventually falls because there's model bias. This digital twin is not this nonlinear model. TD3D3 swing up, you kind of see some of the same behavior as the DDP algorithm that failed because it was initialized in the envelope, but you also see some of that reward hack behavior where it's trying to go to the edge of the boundary to accomplish a swing up. What's really interesting at the very end is the PPO. The rotary arm goes to the edge of the envelope and it swings back and forth, just twirling the inverted pendulum around. So from here, we tried tuning the hyperparameters. We had a working DDPG. We wanted to get the other algorithms to work. And as you can see, we focused a little bit more on the TD3 because it's so similar to the DDPG. And what we tried doing, we adjusted the width of the network, and we just adjusted the hyperparameters a little bit at a time. And we tried to pull from other projects what seemed to work for other projects. As a control, we also took the DDPG geometry that worked and widened it and changed some of its hyperparameters as a control. Now what we have, you've already seen it, some of the same behavior. Increasing the width of the network, changing some of the hyperparameters did not work. They all seem to find that envelope at the edge where they tried to balance the pendulum. Some training observations. One thing we noticed while training these algorithms is that for some of these training sessions, you would get some behavior you wanted, you'd get a better average reward, it'd get closer to the Q value, and then it would diverge. You can kind of see that in this scope. Right here, see the top scope is the rotary angle, and it was going to the edge. Right here, you have the value you want. They're all dead middle. But then the rotary angle starts keeping the inverted pendulum balanced by going to the edge of the envelope. So that happened for several training sessions. We have a TD3 and a DDPG here, and you can see both of them. The light blue and the dark blue get closer to 0, and it starts having good behavior. It looks like you have a good policy forming, and then they diverge. And another interesting note, the reason we're showing DDPG is that yellow, that orange value is the Q value. You can see where DDPG is overestimating that Q value, but the TD3 is not. It keeps it leveled, and that's one of the key differences between TD3 and DDPG. Now, my hypothesis is if the global stop training criteria during these training sessions was set different, or I bailed out while we have that good behavior, and it looks like a good policy is forming, we would have a successful algorithm. So, discussion. From what we had, DDPG was the most successful algorithm on the system. Hyperparameter tuning alone and additional complexity will likely have little effect on improved performance. So far, performance has been dependent on the agent finding a good policy. Also, some of the failures we've seen are a result of reward hacking in the model, and that reward hacked behavior does not work on the actual digital twin due to model bias. For future work, we're going to pull away from changing network size and adjusting hyperparameters. We want to focus on the reward function. We want to try adjusting the weights of the reward function to further disincentivize unwanted policies. There's also the possibility of adjusting the reward function structure, as well as, of course, adjusting the weights for this reward function. We also want to adjust stop training criteria to incentivize a desired policy. So this can be both done within the simulation and can be done globally, such as the average reward. You can change the value of the average reward where the training stops for the agent and all the episodes are complete. We can also adjust the reset function to work with any of the above to help incentivize that desired behavior. And of course, eliminate model bias by training directly on a Quanser digital twin. In conclusion, from experimenting on this system, these algorithms are very sensitive to the reward function and very sensitive to the training conditions. They have outlined weaknesses in model-based training and presented examples of reward hacking and model bias. While successful, these successful algorithms have been sensitive to hyperparameter tuning, the DDPG, and while unsuccessful, it's been indeterminate. We've adjusted the hyperparameters. Unsuccessful algorithms were not successful. While the systems can be successful, they can be sensitive, unstable, and very sensitive to many factors. And in many ways, the training of a successful algorithm is very heuristic and requires some luck. Thank you.